Granite forms when minerals in the crust melt, then react with water, cool, and crystallize. Because it is made of lighter minerals, granite is less dense than other rock in the mantle, so it floats on the surface and mixes with other rocks to form rafts of land. The Volcanic is not totally built from granite. The oldest rocks here are these amazing pillow lavas exposed along the Komati River. 3.5 billion years ago, they form under the sea as lava emerges from an underwater volcanic vent. Upon contact with water, the lava immediately gains a solid crust, which then cracks and oozes additional large blobs called pillows.
These rocks are amongst the oldest that we know. It's basically identical to pillow lavas that we see on a recent ocean floor or in settings like Hawaii.
The Komati pillow lavas begin their life on the ocean floor, but are pushed up out of the sea to form part of a continent. But where did the granite come from? To create it, you need the right mix of minerals. A new theory suggests that life itself may have provided the missing ingredients. It may sound like an outlandish idea, but there's some evidence that living organisms that use photosynthesis appeared around the same time that the continents began to grow, 3.8 billion years ago. Scientists suggest that early organisms, microbes, help speed up the breakdown of rock emerging at the Earth's crust. Over hundreds of thousands of years, this rock breaks down into new minerals, which sink back into the mantle. Deep below the surface, they heat up and form granitic magma. The magma rises into the protocontinent, freezes, and forms huge solid rafts of granite. Now stabilized, the craton begins to grow, forming new baby continents. But cratons are not the only factors at work. More powerful forces are building up deep within the planet. Forces that have the power to rip apart landmasses and smash them together, changing the face of the planet forever. Four and a half billion years ago, the Earth forms. For many years, it is bombarded by asteroids and meteors. Slowly, the molten planet cools, and small landmasses form around cratons of granite rock. Massive forces from deep within the planet rip apart and smash these small protocontinents together as they grow into the large landmasses we see today. The surface of the Earth, the crust, is made up of a giant jigsaw of interlocking pieces called tectonic plates. The separate plates themselves sit on the mantle, the layer between the crust and the Earth's core. Although the mantle is made of rock, the heat and pressure deep down mean it's flexible enough to allow the plates above to move up to several inches a year. Evidence for the theory of continental drift was first proposed in 1912 by German scientist Alfred Wegener. He noticed that identical fossils were discovered oceans away from each other. Paleontologist Professor Mark McMenamin of Mount Holyoke College in Massachusetts is an expert in fossil records.
Wegener noted that a freshwater organism cannot cross a salty sea, and so if you find the fossils of a freshwater organism or a land creature on two continents that are now greatly separated by distance, they must once have been closer together.
By identifying like fossils on different continents, scientists can map which continents were joined in the past.
The fossil distributions will tell us where fossils occur and how the continents must have been juxtaposed. Fossils that are identical but occurring in very different parts of the world imply that the continents have drifted.
When he first proposed his theory of continental drift, Wegener was laughed at. The idea that continents could actually move was considered preposterous. The problem was, he didn't know how the continents moved. The missing mechanism wasn't discovered until the 1960s. Plate tectonics is powered by heat.
Plate tectonics is being largely driven by the fact that the interior of the Earth is much hotter than the surface.
The temperature at the center of the core is 10,000 degrees Fahrenheit. It's as hot as the outer parts of the sun. Much of the heat is left over from the collisions and massive bombardment during the early days of the Earth. The rest comes from radioactive decay of heavy elements in the core. Heat escaping from the core creates convection currents in the next layer of the Earth, the mantle. The process is like a lava lamp, where heat from the bulb at the bottom creates convection currents in the oil, pushing the synthetic lava upward. The heat melts part of the mantle and sends plumes of magma, molten rock, rising to the surface. It rises between cracks in the plates, creating new rock that pushes the plates apart.
I think that plate tectonics is virtually inescapable on this planet. It's an exceedingly efficient way to cool the interior of the Earth.
This formation of new rock splits apart and separates the plates and the continents sitting on them. Today, the majority of this new rock forms under the sea, creating vast interconnected volcanic mountain ranges that extend through all the major oceans of the world. One range can clearly be seen at the bottom of the Atlantic Ocean, along the Mid-Atlantic Ridge. It stretches more than 12,000 miles from the sub-Antarctic to the Arctic. It comes to the surface in a few places. Iceland was created from volcanic lava, bubbling up at the junction between the North American and Eurasian plates. It's one of the few places on Earth that one can actually see continents being pushed apart.
We are watching here geological structures that you cannot really watch anywhere else. It's like a big textbook of geology. This is where the Earth's crust is being made.
Pál Einarsson, professor of geophysics at the University of Iceland, monitors the mid-ocean ridge where the continental plates are splitting apart. The ridge in Iceland is almost 3 miles wide. On one side is the North American plate, on the other side, the Eurasian plate. The rift here grows as new rock forms at its center, pushing North America and Europe away from each other. The Atlantic Ocean widens, and the two continents drift apart. Eventually, the Atlantic could become as big as the Pacific. To measure how fast they're splitting, Einarsson takes global positioning system readings at specific points along the plate margin.
We put the antenna right on top of the point, and then we can calculate the exact position of this point in the world with respect to the center of the Earth.
Although the ridge appears calm and there's no magma rising to the surface, Einarsson's measurements show that the two continents are drifting apart by around an inch a year. So by the end of the century, Europe and America will be almost 8 feet further apart. The movement in Iceland is typical of the processes shaping the continents since their birth 4.4 billion years ago. It's part of the great cycle of the Earth's continents. The new crust, created at the mid-ocean ridge, moves away, cools, and eventually sinks back into the Earth. When the first proto-continents formed, there were several interconnecting tectonic plates, constantly bumping and grinding against each other, pushing the new land over the planet. Today, the Earth has over a dozen plates, some colliding together, some moving apart. They are powerful enough to move a continent the size of North America over 3,000 miles in 200 million years. That's 15 miles every million years. The Earth, 3.4 billion years ago, and plate tectonics pushes the proto-continents together. They combine to form ever larger tracts of land. Scientists suggest that cratons combine with other cratons to form a supercontinent, a huge continuous stretch of land. It's called Valbara. Scientists are unsure of its exact shape or size, as only a few pieces, like the craton in South Africa, still remain. But Valbara's days are numbered. A rising plume of heat is growing beneath it. It's about to rip the world's first supercontinent into pieces. $2.7 billion years ago, Valbara, the world's first supercontinent, still dominates the planet. But plate tectonics, powered by heat from the Earth's core, is about to split it apart. Rock is a good insulator. When a continent gets very large, the rock traps heat beneath it. As it gets hotter and hotter, a plume of superheated magma builds up beneath the giant continental mass. The temperature continues to rise, and pressure in the mantle increases. Eventually, the crust can no longer contain the pressure, and the hot lava breaks through, ripping the land apart. You can see this process happening today in Africa. Heat from the Earth's core is ripping the continent apart. A giant rift valley runs from the Red Sea down to Mozambique. Giant cracks are opening up in the land. Volcanoes, like Kilimanjaro, mark spots where molten rock have risen to the surface in the past. In 10 million years, the eastern half of the continent will have split away. The molten lava trapped beneath the giant supercontinent of Valbara eventually smashes through the surface rock. The continent ruptures into several smaller pieces. These bits of land sail across the Earth. But nobody knows what happens to them or what the planet looks like at this time. The Earth is entering the Dark Ages. It is over 2.5 billion years since it was formed.